The recording, and now it works. Right, today is the last day of the class, and then thank you for your hard work on the class and then labs assignments. And then this part is not in the exam and then nor for the lab assignments, so just takes it and then have fun with the contents. So today I will just introduce how we can debug operating system, and then describe a little bit about how the modern virtualization is implemented, and go over the class review at the end. So let's start with the debugging an operating system. So in implementing JAWS project, we have used the GDB a lot. And then the interesting part is that the question is who will learn debugger? So to think about it. So now we are developing in a virtual environment, but that kind of the virtual environment, including QEMU or that kind of tools, are not available in an old days. And then in an old days, when we are developing an operating system, operating system is just a program, and then we can ship that into the computer machine. And then if that has a crash, then we need to reboot the computer. Yeah. And then another thing to think about is in a computer, in an old days, they just have one single core in the CPU. Then they were running and then got fault. Then who will run the debugger? Because the debugger itself is a program, then there should be a CPU to run the debugger. Then yeah, who will run the debugger? So then let me explain the edge by edge. So an old-fashioned way of still using a lot of embedded systems. So embedded systems are referred to some of the computers inside of that kind of projectors or cameras or Wi-Fi routers. So these days they are all just the computers. So they are running ARM or MIPS CPUs, and then they run sometimes Linux, fully blown the operating system, or something like that. So they are just an operating system. So they need to be debugged, and in that case, we still use this kind of interface, so-called the JTAG. So the JTAG is the name of some of the group, and then that is also used for name of the some interface. And then the JTAG interface is standardized by the IEEE, and then it's a standardized protocol, and that allows having a direct access to chips. And chips are including the CPU. So what it does is suppose this is a NVIDIA's development board, and then there's a CPU, and then there is some of the connectors that we can connect some of the lines, and then these lines on the PCB will be directly connected to the CPU, and then CPU exposes some of the pins on the chip for the debugging purpose. And then what CPU does is it just let the other CPU or other device. So we will connect another device at the end, and then that device can freely access any kind of the registers and memory used by the CPU. So in this case, the CPU is just stopped with some of the trap or breakpoint or something like that. It does not do anything, but the JTAG on the side, it is being attached and then passively monitors the CPU. But it's not actually passive because they can actively modify the contents of the registers and the memory. So that's how we usually provide the debugging interface. And then the same thing happens on most of the embedded devices. So for this kind of the iPhone device, so it also has this kind of the JTAG debugging interface. And then have you heard about the jailbreak attack, or rooting the iPhone and then freely install all the applications? So that can easily be possible if you have a debugging interface. So think about it. If you can have a JTAG connection to iPhone, then you can set the breakpoint at anywhere in the kernel. And then if that is setting the user ID, then just change it to always 0. Yeah. And then you can have a UID 0, which is root. Yeah, that's free. So what Apple did is when they are developing this kind of phone, they do have this kind of interface on their development board. And then after their debugging testing finish it on the real manufactured device, they just burn it and then nobody can access it anymore. Yeah. So that's actually implemented in starting from iPhone 4. So there was some of the way that we can craft some of the USB cable that can directly connect to JTAG for iPhone up to iPhone 3G, I believe. Yeah. But as a defense mechanism, like that kind of thing was like removed. But the important thing here, this is not a security class, although I'm a security researcher. Yeah. So in the systems perspective, so for this kind of the operating system debugging, we need a separated interface because the machine fully stops. So how we can debug is like we need to connect the JTAG like this, and then there is some of the processor here, and then this will be connected to maybe our laptop or other terminal computers. Then we can attach GDB and then use that. And then you're working on the physical machine. Yeah, that's good because that's the real result. Because if you do emulation, there could be some programming errors. So could be discrepancy between the two environments. But if your operating system works on the real computer, then that's the real thing. That's the good thing. But the problem is that to do that, we need to have a physical board. So for example, if we didn't have QEMU or that kind of virtualization environment, then I have to require all you purchase the development board and then JTAG and then use that, carry that with you, yeah, something like that. But our class is very cost efficient, so I don't have to spend any kind of money for that because all the things are running as software. So we just spend the cost for the running OS2 server. That's it. Yeah, that's good. And then another thing is like thanks to the virtualized environment, we can work remotely. Yeah. So we don't have to carry the board physically. And also, suppose the entire machine got crashed or something, then you need to reboot. So there's a way that you can connect the board to the internet and then use that remotely. But suppose you need to press the power button to turn off and then turn it on again. So doing that kind of thing, maybe not available remotely, then in that case, you need to come through the debugging place, something like that. And then that case is like when we have a triple fault. So the triple fault, we cannot handle it, but in our QEMU, it benignly displays the triple fault information, but the usual behavior of the rear computer on happening on the having a triple fault is just a restart. Yeah. And then so that also entails like we need to go through like BIOS boot and all this stuff. So that it might be a little slower in the real operating system development because like I suppose that not JOS boots quite quickly, like in less than 1 second, it will have a monitor or user program. But to think about the Linux machines and then suppose you are an engineer to write the kernel driver for the Linux. Then if you get a crash, then you need to reboot the entire machine and then wait until your IDE turns on again. So that's quite frustrating. So thanks to the virtual environment, so thanks to the software version of the QEMU, yeah, that virtual machine, then if this kind of thing happens, we can just turn off the QEMU and then run it again. So we can do it very quickly. And then another interesting thing is like in the virtual environment, what we can do is snapshot and restore. So what that means is that I will explain a little bit of details later, but the QEMU is just a Ring 3 application in the perspective of the OS2 server. So although we are running JOS inside there, then JOS has a Ring 0 and Ring 3, right? But that's inside of the QEMU machine. So OS2 server that runs a real Intel CPU, but they do have a Linux operating system, and then QEMU is just a Ring 3 application on there. Yeah. And then the next is about explaining the virtual machines. So like the QEMU is a virtual machine, and that's a tool that we can run any kind of the operating system on as a user program. So you can simply think as like think about the operating system. It's just a program. So we have seen that the OS kernel of the JOS is compiled as a ELF binary program, and we love that. And then we do the same thing for the user level program. In the load I code, we read the ELF header and then load it. So actually the formats and then instructions that we are using, these are almost the same. And then the difference between the user program and the operating system is operating system uses some of the privileged instructions. For example, changing CR3 or loading IDT, GDT, those kind of the memory management. Yeah, so those are like a ring zero privileged instructions. So one of the way to run an operating system on top of the another operating system is just run it. But the problem is that in that case, we will be ring 3 of the host operating system. Then when our program, maybe the QEMU, try to run the ring 0 instruction, it will stop. So to resolve that kind of problem, QEMU is like from their name, it's a quick emulator. So there has been a lot of emulator for x86, ARM, or different CPUs, but in 1990s, most of the systems are targeting one architecture. So there is an emulator for x86, emulator for ARM, emulator for PowerPC. But the QEMU was the one, open source one, that tries to virtualize any kind of the CPUs available on the world so that they can support a list of the CPUs like this. And then they are implementing virtual software CPU. So actually they are not running instructions on the CPU. So whenever they have this kind of instruction, they will call a function to interpret that instruction and then modify the values accordingly to the virtual CPU registers. So that's how they work in high level. And then to give a little bit of the information about the OS2 and then QEMU kind of the setup in our system. So the OS2 server has an Intel CPU, but to run JAWS inside of QEMU, the host CPU don't have to be x86 at all. Yeah, because we are not using like the hardware virtualization. All the instructions are interpreted and then semantically running on this QEMU. So we can even run JAWS inside of this kind of the form, yeah, because we can compile QEMU in ARM computers. Then that Intel CPU runs a QEMU that has a virtual CPU inside of it, and then that virtual CPU runs a JAWS. So that's how it works. And then QEMU is a multi-threaded program, and on a different thread, they can support the debugging feature. So we don't need to attach JTAG. We can debugging on the fly. So that's why it's possible. Then next is about what can QEMU also do. So I just told that like to run QEMU, there's no restriction on the CPU, host CPU. So if you have an ARM CPU, for example, on iPhone, so if you fully hacked iPhone and then if you can install any kind of application, then you can install QEMU compiled for iOS and then run Windows on it. Yeah, that's possible. And then another thing that is possible is, so on your, if you have a MacBook Pro, not the latest, even latest one has this kind of the bar, right? So this bar is running with the Apple designed the T1 chip. Yeah. And it has a different instruction set than x86, but that's also software controlled or something. So the hackers can hack into there and run QEMU or DOSBox, that kind of the virtualization environment, and then run a traditional DOS game Doom. Yeah, that's possible. So this is just for fun, but I just want to demonstrate that the implication of regardless of the host CPU, we can run any kind of the CPU as virtually. Then I'm emphasizing that the good thing about studying computer science is that even for the high-end engineering, we can take a look at the entire implementation because most of the things are open source. Yeah. So I'm actually guiding that whenever you have questions for like that, oh, how can you implement the CPU? Then I'm demonstrating that you can learn by yourself by taking a look at the code. And then from GitHub, there's a CPU.h. Yeah. And then you will see that all the registers, EIP, E flags, and then those kind of information are there. And then LDT, GDT, IDT. Yeah. So these are not available for the programming for us from the CPU, but to maintain the CPU's internal status. So for example, whenever we load LGDT or LIDT, then in a software manner, we can just update these kind of the values to keep track of what our virtual CPU should have. And by doing so, if we follow the semantics of the x86 instructions correctly, then we can match this virtual CPU runs as the same as like the physical CPU. That's basically how it works. So, and then also do you guys know the exact difference between simulation and emulation? So the simulation is like doing the same thing in a different method. So for example, if we have a Windows operating system, then if we want to run that on the Mac OS, then one of the way for doing that is like we can find all the privileged instructions in the Windows binary and then change that to the different instructions and run it. So that will have the same effect, but that's actually simulation. We are not running the intact version of the Windows. And then emulation, I believe the E is coming from the environment. So the emulation is we are not touching the target program at all. So we are trying to replicate the environment. For example, Windows operating system runs on the x86 hardware. So we simulate the x86 hardware, then we are actually emulating for Windows machine. And then to replicate the environment more correctly, so QEMU engineers, they also developed the L1, L2 cache virtually inside of there to make their virtual CPU can have some of the, can expose some of the internal behaviors of the CPU similar to that. So QEMU is more on the side of the emulator to try to emulate that kind of the environment also for the virtualization execution. So what I mean is that to have a correct execution. So for example, to run the Windows and the run Doom on QEMU, you don't have to have like this kind of the cache structure, but they do have that to have the environment more accurate or more closer to the real setup. And then next is about how QEMU works. So I told that on the OS2 server, QEMU is just a Ring 3 application. So this is the view of the OS2 server. All the real hardware is connected directly to Ring 0, and then QEMU is just inside there. So entire thing is in Ring 3. But in our JOS's perspective, running inside QEMU, it looks like this, but the entire of this is actually inside of here. So none of these are in Ring 0. But QEMU virtually create a virtual Ring 3 and Ring 0, and then they control it internally. Yeah, that's how we can run another Ring 0 and Ring 3 in there. And then how it runs is very simple. So if we give the program to the QEMU and then just run it, it will start from the 7C00 and keep following that, right? At the bootloader. And then whenever there's an instruction, we show CLI. Then in our virtual CPU, QEMU just set the interrupt is disabled, something like that. And then when we meet the XOR AX, then just zero out AX register from the registers. So we can just follow the instructions and then semantically making our virtual CPU state to be the same as the physical CPU if they run the same instruction. That's it. So So we virtually have a JOS in the QEMU of the ring 0, but that's actually ring 3 of the OS2 server. So even if your JOS operating system runs in ring 0, they cannot affect on the real ring 0 of the OS2 server. Yeah, that's not possible. And then QEMU is a ring 3, so that this application cannot affect to the embedded process if that is running by other user or something, because that's protected by the host operating system. And then accessing ring 3 in QEMU to ring 0 in QEMU, that's also impossible because QEMU guarantees that the virtualized memory isolation, and then it will internally follow our page table bits for that. So at the high level, it's a very simple design. Yeah, just having the virtual data structure and then keep following it. But the good thing about this kind of implementation is the implementation is easy, and then technically we can run any kind of program written in any kind of architecture. If there is a virtual CPU and then there's some of the functions to interpret the instructions, then we can technically run any kind of architecture compiled programs on any other systems. But the problem is that, think about it. So the execution is something like whenever we have a single instruction, it will call handler CLI, and then it will run few lines of the code to update the CPU status. So that means whenever we run one instruction, we might have run 20, 40 instructions. That means our system could get into 40 times slower, 20 times slower. Yeah, that's happening. So although this kind of design is easy to implement and then requires no change in hardware, so everything is done purely software, that's good. But the problem is that there is a blow up of what we have to execute to have the semantically the same the CPU status. So the implications of using QEMU is that the operating system requires the isolation of the memory, but the operating system requires direct hardware access to do that, because that's done by the CPU's CR3 register and rest of the thing. Yeah. And then, so how QEMU does is like the QEMU just treats the operating system as an application, and then just interpret all the instructions and then run it. So the solution is like the QEMU try to emulate not just for the CPU, they need to emulate the disk, network device, and console, and that's why like we can interact with the QEMU right now. Yeah. But the problem is that we are not actually running the instructions, the same instructions on the CPU. So that there could be the discrepancy between the software version of the machine and the hardware version of the machine, but the emulations try to be like correct. And then for fun, you can think it as, so have you heard about the term called the brain in a vat? And then have you watched it or like know the story of the movie series Matrix? Yeah. So in there are two pills, blue pill and red pill. Then if you take a blue pill, you are still in the dream. Then red pill, you can get out of it. Then think about it. So right now, all you are the living matters. And then can you attest if you are really living in the world or you are just a brain connected with some of the electrical lines and then just faking all the brain signals and the feeling like that you're taking a class in the year. Yeah. So it's something similar to that. So we can create the virtual machine, and then we can also do the similar game that program running inside the virtual machine. If they cannot tell, they cannot distinguish, oh, is this a virtual or a real thing? Yeah. Then yeah, we can implement this kind of stuff. But that there are several ways to identify that we are running in a virtual machine or not. And then that's extremely important in malicious software business. The reason is like most of the malware writers, they do not wish to their programs to get debugged by malware analysts. So what they want to do is like if there's any kind of the debugging is ongoing, they try to hide everything and don't do anything. Yeah. So that makes the debugging of the malware difficult. So in around the 2007-ish, so the most of the malware analysts, so if they try to debug it, malware will not expect the malicious behavior. So what they did is they just spawned a virtual machine, Windows, and then installed a lot of like a sketchy program and look like their systems are easily get hacked. And then malware comes in. If they don't know that's a virtual machine, they don't know it's being analyzed and just unfold all the malicious behavior. So using the virtual machine, we can easily get we can easily identify what malware is doing. But the problem is that malware writers try to identify whether they are running in a virtual environment or not. And then one of the way for doing that is like so the malware writer can query about what kind of CPU that we are running. So if it is just a QEMU setup, then it's just return QEMU virtual CPU, then oh, that's a virtual machine. But that is just a software string, then I can change it to the Intel Core i7 something, right? 2.8 gigahertz or something, right? Then what attackers can do is try to execute some of the defined logic. And then they do know how long does it take in a 2.8 gigahertz CPU. And then if it is virtualized, then that'll be slower than the thing. Yeah. So that there's only one way to detect that. So mostly they are trying to achieve the high speed of the CPU. And then if the virtualized environment cannot perform at that speed, then malware writers can easily detect that. And then another thing is like, if the network connection is available, then what you can do is like we can measure the clock cycles of the virtual machine for 10 seconds, and then try to communicate with the NIST time server, whether that's exactly 10 seconds or 10.2 seconds or something. Then we can see that like the virtual environment is a little bit slower, so we can detect that. And then so the QEMU is not a good way to run a virtual machine because QEMU does a software emulation, so it slows down program a lot. And then at the first, like at the version 0.0.1 is very slow, but they did a lot of optimizations. So for example, if they do have like some of the instructions, and they actually compile those instructions to the machine instructions and then just run it on the fly. So if you have heard about like just-in-time compilation, so that's the same technique. So while we are running the QEMU, instead of interpreting the instructions one by one, if there is a one function, so it's something like compiling entire x86 written function into ARM instruction and then run it, something like that. And then that actually speed up the emulation a lot. So we are now enjoy like around the 2 to 3 times slowdown on the QEMU. Yeah, but still it's quite huge. Yeah. And then this kind of the software method to implement the virtualization is the only way before 2005, I believe. Yeah. So the VMware, that company also uses this kind of the dynamic binary translation. That's the technique name. So that they use that to support the virtual machine. But the result is they were slow. But we are seeing that a lot of the virtual machine applications that we can use for now. So there are a lot of commercial products, and then these are not just for using regular desktop for running Windows on Mac, or it can also be used for the server machines to share one server across like multiple users. So how do we use virtual machine monitors, virtual machine software? So as a personal one, is like to just run it like another operating system for task or for fun or something like that. But the commercial application example is, so the cloud computing is, I believe cloud computing is not possible if there's no virtualization technique. And then nowadays, how the cloud computing works is that, so suppose you need a server computer, but in the old days, you need to purchase one of the computer, or you need to rent the entire single computer to have the control over the operating system. The reason was, think about it. So if there's a big computer like this, and then if you want to share this computer among the multiple users. So think about OS2 server. Right now, what we are doing is like we are not giving root permission to you. So you cannot install privileged the applications. So to do that, you need to ask the administrator, and the administrator to do that for you. So in an old day of like the sharing one of the server machine across the multiple users. So nowadays we call it as a platform as a service cloud. But what that actually do is like it does not give the operating system privilege, just install the application and run. And then those applications, even you cannot install just, and then you need to reuse. So use the existing applications on the server. But with the help of the virtualization, what you can do is like even if we have only a single machine, we can run a virtual machine monitor, and then we also call that as a hypervisor. And then that can manage to run multiple operating systems on top of it. And then these operating systems are running in a different process. And then we have learned that two different environments, two different process will have a different page directory. So virtual memory is completely isolated. So the one tenant on the machine cannot affect to the another machine. And then all the access control and those kinds of security control is done by the hypervisor. And then technically hypervisor runs as a ring 0. And then these are runs as a ring 3. And then that kind of isolation is here. So this is the technique that how we can enjoy the sharing the one machine among the multiple tenants on the cloud machines. So this is about that kind of the content. And let's take a look at how it works. So without virtualization, we have the OS kernel, and then we run the ring 3 application. But if we have a virtual machine monitor, so it changes something like this. So we are adding a ring level at the bottom. So the lowest, the highest level, the lowest number was 0. So we just add ring -1. So it's not -1 actually, but conceptually we call that as a -1 because the ring, so it should be lower than ring 0 to have a much more privilege. And then how it works is something like this. So the hypervisor works as an operating system, and then they regard all the operating system as an application to them. And then internally, it will have ring 0 and ring 3 to run the operating system prepared. And then previously I told that so without the hardware change, we only have a ring 0 and ring 3, so we cannot have this kind of competition without having the translation on the software. That's why QEMU is slow, and then these are the interpreting all the instructions. But to enable the cloud computing and then speed up the performance of the virtualization, both Intel and AMD, they inserted new instruction sets to support the hardware virtualization. So that means instead of running the guest operating system in a ring 3, they are actually running the guest operating system in ring 0. Then without any modification, all the instructions runs on the real CPU. So their performance overhead is less than 1%. It's super fast, right? Because it previously was like 200% overhead in QEMU. So the virtualization gets quite cheap after inserting those kind of instructions. And then to introduce what kind of instructions are there. So we learned that the switching from the ring 3 to ring 0, we can issue a software interrupt, or we can use syscall sysreach for the 64-bit, and then sysenter, sysexit for 32-bit. Although we did not cover syscall, sysenter, but you can think it as the same as like this kind of the interrupt handling trap, and then we can get the trap frame and then control over all the environments. Yeah. That's the thing. And then Intel and AMD, they inserted two instructions called VM-exit and VM-enter. It's very similar to sysenter and sysexit, right? So The detail is a little different, but at a high level, conceptually, the hypervisor treats operating system as a Ring 3 application. So there could be system call-like interface between those two. So they just inserted these two, and then they are managing the similar trap frame for virtual machines. So right now, JOS has the trap frame for environment, the process. And then in this case, hypervisor need to maintain their trap, and in their trap frame, they need to store the information required for running the entire virtual machine. So the specific code for handling the trap is a little bit different, but at the very high level, how we can switch the ring and then interact is very similar to that. And then from the operating system to hypervisor, because the hypervisor owns all the hardware access, there should be some of the call similar to the system call. So in operating system, Ring 3 doesn't have the hardware access. So we need to make a system call to let the operating system do that for us, right? Then similarly, this kind of the VM exit and enter is so-called hypercall. So this is the system call, and this is the hypercall. And then theoretically, we can nest it infinitely so that we can run virtual machine monitor inside of there. We can run another virtual machine monitor and so on. And then we can run like the 100 dApp and then run those. That's also possible. So I've done that for running Zen, VMware, and Windows. Yeah, that works. And then for handling the hardware interrupt, so the user, Ring 3, will invoke a system call. And then that will be coded by the guest operating system runs in Ring 0. And then that operating system to really access the hardware, they will invoke the hypercall to access the virtual machine monitor, and they will handle the request and then get back. So you can think it as there's a one more step to access the real hardware and the running the operating system bare metal. Yeah. So these are the information of the VM exit and VM enter, but the important thing is that it's very similar to interrupt 0x30 and IRIT, sys enter and sysert, those kind of things. Then, so Intel actually, they just added these kind of two instructions, November 2005, I believe. Yeah. And then AMD followed that kind of the virtualization implementation because they are sharing the architecture instruction set. So, and their implementation was quite late, 2006 April or something, but they do have a different implementation. And then that's actually for address translation. And then let me describe about that. So I told you that the hypervisor will regard the entire guest operating system as Ring 0, right? So in the hypervisor's perspective, these are Ring 3. Yeah, entire Ring 0 is Ring 3. So hypervisor has access to the physical memory. And then guest operating system do not have access to the physical memory at all. Then there should be a translation between the guest operating system and the hypervisor. And then we already have the virtual to physical address translation from the guest user to guest operating system. So that previously we just learned the address translation. So like think it as like this is the guest virtual address. This is the guest OS physical address. And then this is the real host physical address. So if you hide this part, these two parts is just the same as JOS, right? Virtual to physical address. But now our operating system do not have a physical memory access. Then there is another level of the translation. Yeah. Then let's think about some of the problems in the translation. So in this case, we are not trying to emulate the execution. We want to run the operating system on the real CPU. And then for the first thing, so to translate from the guest operating system to the hypervisor's physical memory, we definitely need a page table. Okay? Then where should we store that kind of page table? So we can store that page table from the guest physical address to the host physical address in here. And then when we are using JAWS, ring 3 has the page table and the ring 0 physical memory. And then this kind of translation can be handled with this page table. Then let's take a look at what happened if we run the hypervisor and an operating system on the bare metal CPU. So to have this kind of translation, we need to set the CR3 of the CPU to point to the physical address of this one. Right? This is okay. And then when we run VM enter, then our CPU will start running on the guest operating system. And then to handle this kind of translation, we need to set the CR3 register to this page table. So that makes sense. But the problem is that, and let me ask you one question. So CR3 register, what kind of address do we need to put on there? Virtual address or physical address? It's physical address, right? Yeah. And then problem is that this is the virtual address to the hypervisor. Yeah. This address space is totally virtual address. Yeah. And then CR3 points to the virtual address. Then how can you translate that? So the answer is actually whenever we have a translation to the guest virtual. So to get the CR3 and the page table, we need to go through the hypervisor's page table to figure out what that virtual address corresponds to the physical address, and then get that. So basically, what we need to do is like these kind of the translation. And then it looks like a little complex, but let me explain that. So this is the example of the nested page table. So the reason why we need to have a nested page table is that we have two page tables. One page table is between the guest operating system and then physical memory. And then the other page table is for the guest user and the guest operating system. And then all these addresses are virtual addresses. So whenever we walk down one level on the page table, so for example, to get the physical address of the page directory, we need to translate this first, and then this, then finally we can get the physical memory. So there's a two translation, right? And then that's only for getting the page directory. And then after accessing page directory, we need to access the page table. And that also involves these kind of two translations. And then this is the diagram for the 64-bit case. And for 64-bit, we don't translate the lower 12 bits. And then we have a 4-level page table. So, and then each of the page directory table can be accessed as indexed by 9 bits, because a 4 kilobyte divided by 8 bytes is a 512, that's 2 to the 9. So 4-level page table can support up to 48 bits of the space. So starting from the guest CR3, so that's actually the virtual address. So we need to translate this virtual address to the hypervisor page table. And then finally, we can get the physical address of the first level page directory. And then after getting that, that's also the virtual address. So we need to translate it again. And then second level, third level, fourth level, then we can get the physical address. So in 64-bit machine, in the normal case, we need to access 4 memory to translate virtual address to physical address. That was not that complex, but when we get to the nested page table, we need to translate 20 times for the address. But this was done in Intel's first version of the virtualization, they do not support the walking down the page table in this manner with the hardware. So software need to handle all of that. So that was so slow. And then later, the AMD in 2006, they implemented so-called nested page table like this. And then their performance was so good. So in 2007, Intel implemented the extended page table. Actually, they are conceptually the same, different marketing term. So this is the history of the thing. Yeah. So I just briefly introduced a little bit of the things of the virtual machines, and then is there any questions about that? Yes.
Is that for extra credit we can get JAWS to a virtual machine on like the Raspberry Pi? But if it's a ring-free application,
so if you run JAWS QEMU on Raspberry Pi, that's super easy. Yeah. But the opposite would have an extra credit. So on JAWS, can you run ARM operating system? So on JAWS, can you run MS-DOS? So that's actually possible because, so this JAWS project originally designed by MIT from like since 2005, I believe. Yeah. And then around the 2011, 12-ish, some of the researchers at the University of Texas and then North Carolina and where's that, Stony Brook, they designed a different version of the Lab 4 of JAWS. So until Lab 3, we are doing the same thing. And after creating the environment, their JAWS Lab 4 is building a virtual machine monitor. And then what they can do is after building a good virtual machine monitor, they can run JAWS virtual machine monitor and then run JAWS on top of it. Yeah, that's possible. And also not JAWS, they can actually run another operating system on top of it. So you can get 200 points extra credit if you implement the JAWS virtualization and then run those and run Doom on it. It will be super fun. Yes. I'm not sure. I haven't tried that because in some of my research project, I have done like a cache side channel attack and then report to the Intel and then successfully hack that. But I just tried to the real hardware. And then I believe like definitely the behavior would be totally different. Yeah. And then the cache replacement algorithm, that's a secret. And then intellectual property of the Intel. Yeah. That's why all the hackers need to reverse engineer those stuff. And any other questions for general in operating systems and others before we moving to the last part, the final summary of the class? Yes. Pardon? Yes, I have done that. Yeah, when I worked with the like Xilinx and then like FPGA or that kind of thing. So actually, my undergrad thesis was like the building a password cracker, and then that requires on the FPGA I need to build a CPU, and then I need to upload the CPU and then run the operating system on it, and then in doing that I need to debug that operating system, and then so that I actually JTAGed the CPU that I designed. Yeah. And then one of the good things is like thanks to the advances in the compiler techniques. So in old days, not that old, like the 2005, 6, and that at that time. So compiling a ARM program in the x86 system was a headache. But then nowadays, like it's not a matter at all. Yeah, because like we have a tool chains are available for the most of the architectures, and then we usually call that as a cross compilation. So compiling for the board machine from the x86 kind of thing. Yeah, but nowadays, like the developers are not that stressful for doing that. So in 15 years ago, whenever there's a keyword for the cross compilation, then like everybody like feels about the headache and then traumatize themselves. Yeah, but with thanks to the virtualization and the compilation techniques, so we don't have that kind of headache anymore. Right, if there's no further question, then let me move to the final summary of the class. So I believe like the 10 weeks are quite short because like I borrowed this JOS project from MIT and then their schedule is on 16 weeks base. So that's why the lab has like the entire 6 labs, but we can only finish 4 labs within 10 weeks. So that was the little unfortunate thing, but I tried to deliver the most of the important parts of the engineering details of the operating system within the class. So we started with the booting, and then we learned about the very old way. So starting from 1979 or something, so that kind of the boot procedure. And then that actually works for today. So if you disable the UEFI or and then enable the legacy boot, and then that's actually the taking the same steps that what we have seen in the QEMU and the debugger. And then we learned about how the entire boot process is going. So in an old days, there are not much fancy things at the start. So we just fixed the first sector should have the boot record. And then from there, we load the kernel. And then in week 1, we learned about how we enable the protected mode and load the kernel. So that you can also see the answers of each questions to this slide. So please use that for checking that whether you thoroughly learned about the things in the class. And then we learned about the little bit of the address translation. So we learned about the segmentation and paging. And then the segmentation is obsoleted right now. So still in 32-bit, it has a segmentation, but starting from 64-bit of x86, there's no segmentation at all. Yeah, we just use the CS register to keeping the ring privilege. Yeah, and then we are not actually using the segmentation. So inside of JAWS, what we have done is actually the same. So for the segmentation, we just enable the full memory range from 0 to 4 GB as available range. So that's actually like if we are completely ignoring the feature of the segmentation. And then the modern operating system using implements a virtual memory. And we learned about the why virtual memory is useful and required. So we could have transparency, isolation, and what is that? Reducing the fragmentation for the performance and then efficiency, right? And then that kind of the page table structure is not linear. We have a tree-like structure to minimize that the metadata data structure for the page table. And then because the page table workdown requires a 2 memory access in 32-bit, 4 memory access in 64-bit, and then 20 memory access in 64-bit virtualization. To avoid that, we have a cache in the CPU called the TLB. And then we learned about the cache coherence a little bit about when we learned about the lock and synchronization. There was a lot of cache invalidation miss, but TLB is not managed with the cache coherent protocol. So that's why whenever we update the page table, we need to invalidate TLB. So that kind of the invalidation will not automatically shipped by the CPU. And then in week 3, we learned about how operating systems lay out the virtual memory space. So the interesting point here is that we are not separating out kernel memory from the user memory. So in a single page directory table, we have both kernel and user. And then how we arrange the memory is that we put the most of the kernel part at the high memory on top, and then lower memory uses for the ring 3. And then the actual mechanism that separates out the kernel and user is actually the bits in the page table for the PTU or not, and also bits in the CS register for ring 3 or ring 0. And then we also learned about some of the engineering details about like we set a page size as a 4 kilobyte. That's why we can ignore this 12 bits. And then 4 kilobyte page is magically have a 1024 entries. So that can be indexed by 10 bits, 10 bits. So like these kind of the 10, 10, 12 separation, I believe that that's intentional. Yeah. And then like I'm not sure the exact reason for the kind of number, but for that era, 1985 or before there, so 4 kilobyte, and then this kind of design was like the particularly performant, I believe. Yeah. And then we don't have to stick with that, and then we can have like a different designs. So that depends on the what kind of workload or what kind of constraint we have in the system. So what I'm telling that this kind of the 4 kilobyte page size, 10 bits for index, these are just a arbitrary thing, but decided by with the consensus among the engineers. So this can be easily changed. So if you want to design your own CPU, then you can change it as like a 6-bit indexing or 12-bit indexing with the bigger page sizes. That's possible. And after having those kind of thing, we learned about how the user kernel execution switch may happen. And then we learned about the ring privilege level. And because we isolate the kernel and user using the memory and the privilege level, so ring 3 application can never have direct access to the hardware. And then all the things need to be mediated by the operating system. And the interface between the operating system user is so-called system call. Yeah. So you can take a look at the more detailed answers for those things in here. And then to support the system call, we need to have a method to switch from the ring 3 to ring 0. Yeah. And then not just for using long jump, because long jump only allows we get into the or user application and then return. It's not about the ring 3 can be on the ring 0. So we use interrupt as that kind of the ring transition mechanism. But interrupt is for handling faults or exceptions and those kind of things. So for the system calls, they do not have to use interrupt routine. And then interrupt routine indeed like the effects on the execution of the pipeline and then some others on the CPU. So starting from 2002-ish, starting from Pentium 2 processor, yeah, so Intel and AMD inserted so-called sys-enter, sys-exit. So what it does is actually very similar to the interrupt routine, but they ignore some of the things that CPU have to flush if that's the real interrupt. Because system call is a fake interrupt, so we don't have to do that. So that's why Intel and AMD designers create a different routine, and then omitted that kind of the useless, unnecessary operations for the system call handling. And then that kind of the interrupt handling can be configured with the interrupt descriptor table. Then we can set that. And then having a flag for the ring 3 here allows ring 3 application can interact with the kernel. And then we also learned about how to create this kind of thread handler and the link with the software systems. And then I have one question to you. Have you felt in writing this kind of the thread handler and interrupt descriptor table, have you felt that like it is designed in a weird way because there could be better way to put the interrupt descriptor table, right? So in implementing this kind of thread handler, we intentionally put the push 0 if there's no error code, and then we need to create the function per each interrupt or something like that. Yeah. So the reason is, so when the hardware was designed, they have a little bit of the purpose to use that. but they don't know what will be the entire thing that they can do. In the most cases, so when the CPU designer announces one of the features of the hardware, what happens in the wild is like that. So system designers are very clever. They try to repropose that hardware and use that in a completely different way to do something else. So the copy and write fork is one of the thing like that. So we didn't expect that happens using when developing the paging. Paging is just for virtual memory, and then system designers can implement the different techniques on top of that. So the implication is that although hardware is designed in a limited fashion, with the help of a little bit of the tricks, engineering tricks and coding, so that we can enable the many different features. Even the original engineer who developed that instruction have never thought about. And then after that, we try to understand the trap framing, and then we play with the thing to identify that where to debug, and then taking a look at the error code, those kind of things. And then after learning about the interrupt, I demonstrate some of the cases that we can implement the copy and write with the page fault handler. And then another use case of the page fault handler could be we can automatically increasing the user stack if the page fault happens near the available stack, or we can implement copy and write, or we can regard the disk as memory, and then we can make it entire operation transparent. So the Ring 3 application, they may have like a little bit of delay on execution, but they don't have to care about the limit of the physical memory size. So physical memory plus the disk size can be a total memory size with the memory swapping. And then thanks to the page table and paging, we can implement that seamlessly. And after learning about the isolation a lot, and then we move to the synchronization. And then data racing is the case that the two or more thread try to access on the data, but if there's a two or more writers, and then there's a one or more readers at the same time, then there could be a data racing. So to avoid the data race, we need to synchronize the store of the thread that runs first and need to be finished before the next thread read the value. And to guarantee that kind of the storing reading order, so we can have a critical section. And a critical section is a section that only one thread can execute at one time. And then we can implement the critical section using mutex, which is a lock, which only allows that one thread can move forward. And from there, we also studied about how we can implement lock. And we cannot do that purely software manner if there's no atomic instruction provided by the CPU. Then for Intel CPU, they do have exchange instruction that's the atomic instruction, and then also has a lock on the memory bus. So by using that, we can create a critical section. And then we have gone through like the 5 different lock implementation. Pure software one was not that great. And then exchange one generates lots of cache miss. So that's why we have a test and set. So Intel did a bad job on there. So we can implement it in a software manner. And then to reduce the more cache miss, we can apply the exponential backoff. And then all the things are the same similar to what people at Mutex have implemented. So, and then another thing that I want to emphasize is like the things you learned here is not the fake one, the real one. And then I try to mimic as like this, as similar to the reality, to that. And after learning about the lock and mutex, and then we learned about some of the cases, the problems caused by those kind of lock, and it's called the deadlock. And then there could be a case that some of the threads try to greedily acquire the log. They compete each other, so there's a case that nobody can move forward. Yeah. And then we have learned about how we can avoid those kind of the cases. And then I believe one of the easy practice is that these four cases are not independent at all. And then we have gone through the examples, and then we saw that most of the cases are solved by MATLAB. Yeah. So I highly recommend, if you don't know how to resolve the deadlock, then try to think about using MATLAB. Then it's performance-wise, it's not that great, but at least it can make it run. Then after that, think about some of the different solutions for that. So as a final remark, what I want to emphasize is that in this class, yes, I asked you to do too many things, I know, but that means like you learned about the many things from the computer science and system stuff in this class. So you just go through about like the building an operating system by your hand in a nutshell. Then starting from bootloader, and then you know how to set the virtual memory and how to set the interrupt handlers, system calls, logs, and then copy and write fork, yeah, and then preemptive multitasking. Yeah. So if somebody asks that, like, do you have experience in the terminal IDE tools? You already have that. You practice it in this class. Yeah. And also, if somebody asks that, have you ever done like a kernel level programming and kernel debugging? Then yes, it's a toy operating system, but we actually did that. Yeah. And then the development environment for Linux is not that different like this. So the only difference is like inside of GNU, we need to load Linux. That's it. All the other tools or how we use GDB, how we set the breakpoints, these are all the same if we work on JAWS and we work on Linux. Then, so if some of the job interviewer, they ask about like questions about these kind of thing, and then I believe that you can easily answer for these kind of thing. And then another thing that I want to mention is that the real heroes of this class is like TAs. So the reason why I request many TAs, so usually the school gives the one graduate TA for 70 students. So we have 200 students in this class. I can only have 3 TAs. And then I actually requested 7 TAs. The reason why is like there are many students who don't have a good background on the C and C++ or like this kind of debugging. But I do not wish that stops learning about the operating systems. So what I have seen after I came to OSU was like there was an operating system class, but because some of the class is not thoroughly teaching about the C, GDB, that kind of debugging. So the previous class that does not like handle about like the GDB debugging or this kind of the thing. Yeah. And then so this is the 5th time that I offer the class, but I believe it went well. But at the first time, like I mostly like the work around the 14 hours a day to handle all the questions from the Discord. But nowadays the TAs are trained well, and then we have an archive of some of the pinned messages. And then I also want to thanks to the students who also pay forward their help to the other students. Yeah. And then we all together make the things good things happen in this class. And then so this is the photo of one of my graduate students. And then this student has no previous CS background at all. He was he has a BS degree in the mechanical engineering, and then worked in some automotive, the mechanical design or something, and then entered the grad school in 2019. And then I always liked learning something in a hard way. So I asked him to take my class and then study hard for the operating system. it's okay having no background at all. And then after 10 weeks of the study, he coded like a pro. Yeah. So he enjoys this kind of the wide monitor, and then like they often a lot of terminal tools, and then now he's very good. So what I want to tell you is that you also learned a lot of things in this class. So please be confident yourself for you have learned a lot of things in the computer systems. And then please work as a pro like this. Yeah, I'm not telling that you should work like using the terminal or something, but what I'm saying is that now you know how to use Git, Emacs, or some terminal tools. And then I also like that they're using VS Code for editing the code, because that's a good text editor, and then that could be a good idea. Yeah, and then so what I want to emphasize is that it's okay to use a different tool and then your own tool or something. Then uh, like what I want to tell is like I know not all students, and then many students are here for like embracing the difficult stuff, but I've seen that many students, whenever they see assembly, they just go or walk away. And then whenever they hear about kernel programming, just walk away. And then what I want to tell you is that don't do that. Yeah, computers are easy. They are dumb. Humans are more smart. You guys are more smart. And then after you understand the concept, if you practice it with the real programming, then yeah, it's tough. But after that, that's all yours. And then I believe like now, many of the students will feel that maybe if I write a code for JOS again, then I can finish in 1 week. Yeah, that could be possible. Yeah. So please be confident about the operating systems. And then next time you hear about the kernel debugging assembly, then volunteer that I can do that. Yeah, that's what I want to see for when you get a job and work it there. So the final thing that I want to mention is that so I removed all the penalties for the assignments. So please finish all the assignments on December 9th. Yeah. And then after that, I will work on the grading and then give the final grade. So I cannot accept the assignment after that date, but that's the final due date. So please work hard for that. And another thing is like our JOS is the real operating system. So if you bake it in a USB drive, you can actually boot on your laptop. But the problem is that right now it is set as a 32-bit. So your laptop has more than 4 GB of physical memory. So JAWS might not catch that correctly. So N pages or that kind of thing will overflow all the like that, all the data structure that we have. So what you need to do is like the JAWS internally runs some of the function calls to the BIOS to get the number of the available pages or total maximum memory, that kind of thing. And then you can forcefully change those values to just use 128 megabyte or 256 megabyte. That's the maximum memory that JAWS support. Then you can actually boot your JAWS bare metal. But if you want to do so, please don't forget to change your BIOS option to support the legacy boot mode, because our JAWS does not support UEFI boot for now. Yes, and this is the end. Yeah, thank you for your attention and hard work, and feel free to ask any questions at the last moment. Thank you.